but it's a method when you have a constraint. You could also use the methods we were just talking about when you have constraints. It's just if you have some exterior constraint, this idea that's presented and it's given the name Lagrange multipliers can also work. But all the problems that I'm going to do in this set of examples, you could set up a min-max, find z sub x, find z sub y, find your critical points, find d. You could do that, and then after you did that, look at your constraint and reason out the answer. But when you do have a constraint, you can also use this other method. And the premise behind the method is that if you have a constraint, the constraint is going to create a max or a min where its contour is tangent to the contour of the surface. So the two surfaces, the constraint equation surface and the other function's equation surface, where the two of them are tangent is going to be where you're going to hit a max or a min point. So notice that the contour, the blue curve is the constraint. So the contour is tangent to the contours of the surface. So the pinks are a bunch of contours of the surface, and the blue is showing you a contour of the constraint. Notice it's not the maximum value of the function itself, because the function here is 11, whereas where they're tangent it's 10. But in terms of where the constraint is crossing the other function, where the two are tangent is where the function's hitting a maximum relative to the constraint. Okay, so you're not looking for the pure max or min of the function. Instead, you're looking for the max or min relative to the constraint. So 10 is the highest value that I could get on this function, given that the constraint also has to be true. Okay, and so some situations have that wrapped into it, where you need to have some second things maintained, and you're looking for the optimum, the max or the min for the surface, given that you have some other condition that has to be held. So if the two are tangent, then the normal vectors to the surfaces, and hence they're also the normal vectors to their tangent planes, they have to be parallel to each other. Okay, so if the two surfaces are tangent, this picture has it drawn so that their normal curves are kind of going out in different directions, but the normal vectors have to be parallel to each other. If vectors are parallel, then one is just a multiple of the other. And so what you do is you find the gradient of the surface. Okay, why are we doing that? Well, the gradient gives you basically the components of your normal vector for your normal plane. It also, if you shrink it down one level, the gradient is perpendicular to your level curves, and so if the two are tangent at that point, then the other curve also has a gradient that is perpendicular. It's just, so they're both pointing in the same direction, but one might be longer or shorter than the other. They're multiples of each other. This symbol here is the Greek letter lambda. There's nothing really special about lambda. It just happens to be the standard letter that gets used when you're working with this method. Kind of like M is the standard letter that gets used for slope in y equals mx plus b. There's nothing special about it. What's important is that you understand, you find the gradients because the gradients give you the directions of the normal vectors to the tangent planes. They also are the vectors that are perpendicular to your level curves. And we know where you hit a max or min, the constraint is tangent to the level curves, and hence their gradients need to be parallel to each other. If their gradients are parallel to each other, they're multiples of each other. So you set up your whole system based off of this idea. Okay, so our first example is just a plain little example. I'll write it up on the. Okay, so in our first example, it's just a generic example, there's not applications. So this method is often good for applications, because applications often have some real world constraints in them, but we're going to start off with just a generic example. So this is my original surface. And my constraint is that x squared plus y squared has to equal 16. Oh, I'm sorry. Oh, no, you're right there. Cubes. Thank you. Sorry, x cubed plus y cubed equals 16. I'll mute it and kind of work from the beginning over. While you guys are jotting that down, let me see if I can pull up that